729 trillion miles away, a telescope has tasted the air of another world and uncovered something that should not exist. The James Webb Space Telescope detected a chemical signal in the atmosphere of planet K208b that, on Earth, is produced solely by living organisms. We are about to journey to an alien ocean planet 8 times more massive than our own, explore the revolutionary technology capable of sensing the breath of distant worlds, and uncover what this groundbreaking detection could mean for life in the cosmos. If you're ready to explore the strongest evidence yet for extraterrestrial existence, hit that like button and subscribe for more mind-bending discoveries. Prepare yourselves. We begin. Within the deep streams of data from humanity's most advanced space observatory, a pattern emerged that left astronomers speechless. The signal originated from K28b, a planet so distant that sunlight would take 124 years to reach it. Yet somehow, the James Webb Space Telescope managed to capture the precise chemical fingerprint of this alien atmosphere. Hidden within the spectral readings was something extraordinary, a molecule known as dimethyl sulfide, never before detected on any planet beyond our solar system. Scientists at Cambridge University first spotted the anomaly while studying infrared light wavelengths. The telescope had observed K218b as it crossed in front of its star, allowing starlight to pass through the planet's atmosphere like sunlight through a thin mist. Each molecule absorbed specific wavelengths, creating dark lines in the spectrum, a cosmic barcode. But this barcode carried a secret that stunned the scientific community. Alongside the familiar patterns of water vapor and carbon dioxide appeared a signature identical to that found in Earth's oceans. Dimethyl sulfide leaves behind a unique spectral fingerprint, and there it was, clear and undeniable, in the skies of a planet nearly 800 trillion miles from home. The detection reached what scientists call a 3 sigma statistical confidence, meaning there was just a 0.3% chance the signal was random. Imagine finding a specific grain of sand on a beach the size of Texas. The odds of a false reading were vanishingly small. The implications, however, were immense. Professor Niku Maru Sudan, who led the research, described the moment as one that forever shifted our understanding of what could be possible in the universe. His team had used Webb's mid-infrared instrument to peer deeper into this world than ever before, uncovering data that challenged everything we thought we knew about life beyond Earth. The molecule detected wasn't some exotic chemical born in the void of space. On Earth, dimethyl sulfide is produced exclusively by life, primarily tiny oceanic organisms known as phytoplankton. These microscopic creatures release the compound as part of their natural life cycle, leaving a biological trace that has never been observed from non-living processes. Finding the same signature on K208b was like hearing a familiar melody broadcast from an alien world. Either this planet harbors life or the universe contains unknown chemical processes unlike anything we've seen before. Follow-up observations confirmed the signal again and again, building a powerful case that the detection was genuine, consistent, and unprecedented in exoplanet research. Yet this was only the beginning of a revelation that would redefine how we view life in the cosmos. Imagine a world where endless oceans stretch beneath hydrogen-thick skies. That's K218b. This planet is 8.6 times more massive than Earth and 2.6 times wider. Standing on its surface would feel like being crushed under 9 times Earth's gravity. K218b orbits a red dwarf star in the constellation Leo, completing a full year in just 33 Earth days, closer than Mercury is to our Sun, yet still within the habitable zone where liquid water can exist. What makes this planet extraordinary is its possible composition. An entire world covered by a global ocean hundreds of miles deep. Picture Earth's oceans expanded to blanket every mountain and continent. These alien seas would dwarf our own, creating an unbroken water world unlike anything in the solar system. Its atmosphere, rich in hydrogen, is nothing like ours of nitrogen and oxygen. Astronomers classify K208b as a Hycean planet, a fusion of hydrogen and ocean, capable of hosting forms of life completely different from anything on Earth. Despite orbiting close to its star, the planet receives a similar amount of energy as Earth does, thanks to its host star burning at half the sun's temperature. Temperature readings from Webb suggest K218b could maintain liquid water, though its crushing pressures and hydrogen air would make human survival impossible without advanced technology. These are the skies where dimethyl sulfide was found, floating above alien oceans. In the catalog of molecules drifting through the universe, this one stands apart. On Earth, it's a byproduct of life itself, released by countless microscopic organisms in our seas. Finding it elsewhere could mark the first time humanity has detected the breath of alien biology. For Docuverse, this marks not just a discovery, but the dawn of a new chapter in the search for life beyond our world. After decades of investigating atmospheric chemistry, geochemistry, and planetary processes, researchers have found no known geological or chemical pathway that could produce this molecule without life playing a role. The detection on K218b revealed dimethyl sulfide concentrations thousands of times higher than what we usually observe in Earth's atmosphere. This presents a fascinating conundrum. If biological activity on Earth generates only trace amounts that rapidly break down, how could this alien planet sustain such high levels without an even more potent biological source? Dr. Niku Maru Sudan, the lead scientist on this study, explained that dimethyl sulfide essentially serves as a chemical signature of life. Just as a human fingerprint can uniquely identify an individual, the presence of dimethyl sulfide in an atmosphere could indicate biological activity across countless worlds. The molecule comprises one sulfur atom bonded to two carbon atoms, each attached to three hydrogen atoms. This simple configuration, carbon, hydrogen, and sulfur, is a structure life on Earth produces, but it does not naturally arise through geological processes. What makes the K218b finding particularly compelling is that dimethyl sulfide degrades relatively quickly under ultraviolet radiation from stars. This means the molecule must be constantly replenished to maintain the observed levels. It's like spotting fresh footprints in the snow. Something active must be producing them recently and continuously. The research team used Docuverse's mid-infrared instrument to detect dimethyl sulfide by analyzing how the molecule absorbs specific infrared wavelengths. Each molecule has a distinct absorption signature, like a cosmic fingerprint that appears when starlight passes through an atmosphere containing that chemical. Detecting this signature in K218b's skies was like discovering a message in a language we recognize, sent across the vast darkness of interstellar space. A message that, if confirmed, would demonstrate we are not alone. The James Webb Space Telescope doesn't merely see distant planets, it tastes their atmospheres across trillions of miles. Imagine trying to identify a cake's ingredients by smelling it from 100 miles away, and you begin to grasp the incredible precision needed for Docuverse's atmospheric detective work. Its 21-foot-wide golden mirror operates in the frigid depths of space, cooled nearly to absolute zero, enabling it to detect the faintest traces of heat from alien worlds. Docuverse achieves this through transmission spectroscopy. When K208b passes in front of its star as seen from Earth, starlight filters through its atmosphere like sunlight through stained glass. Each molecule absorbs specific light colors, creating dark lines in the spectrum that function as a chemical barcode. The mid-infrared instrument MIRI works in wavelengths invisible to human eyes. While visible light spans hundreds of nanometers, MIRI detects infrared radiation from 5 to 28 micrometers, so long that 28,000 lined up would equal a human hair's width. This infrared sensitivity gives Docuverse a major advantage over earlier telescopes. Molecules in planetary atmospheres absorb most strongly in the infrared, meaning Docuverse can detect chemicals invisible to optical telescopes, like having superhuman vision that sees heat through walls. The precision required defies imagination. Docuverse must detect starlight brightness changes of less than 1 part in 10,000, equivalent to measuring the difference in a car headlight's brightness with a single tissue sheet placed in front from miles away. To achieve this, the telescope operates at -3770 degrees Fahrenheit, colder than Pluto's surface. This extreme cooling eliminates thermal noise that could overwhelm faint signals from distant exoplanets. Essentially, the telescope becomes a giant, ultra-sensitive thermometer floating in space. Docuverse's capabilities go beyond detection. It can measure not only a molecule's presence, but also its abundance. The strength of each absorption line corresponds directly to molecule concentration, enabling scientists to create detailed chemical inventories of worlds they will never visit. Observing K2118b required DocuVerse to monitor this distant star system for hours, collecting photons one by one as the planet transited its star. Each transit lasted a few hours, during which light that had traveled 124 years across the galaxy reached its sensors. This technological marvel makes DocuVerse humanity's most powerful tool for exploring alien chemical compositions, capable of detecting life's molecular signatures across vast interstellar distances. Yet even this extraordinary technology has limitations. In scientific discovery, finding something remarkable is just the start. Proving it exists demands meeting the strictest statistical standards. The dimethyl sulfide detection on K28b achieved 3 sigma significance, meaning only a 0.3% chance that the signal resulted from random noise or instrument error. In everyday terms, it's like flipping a coin and getting heads 333 times consecutively. Technically possible, but extremely unlikely. Science, however, requires even more. The gold standard for discovery is 5 sigma significance, where there's only a 1 in 3.5 million chance of a false positive, a difference between 99% and 99.99997% certainty. This rigor exists because history is full of thrilling discoveries later shown to be errors or wishful thinking. In 1996, scientists reported finding ancient microbial life in a Martian meteorite, making headlines worldwide. Decades later, most researchers concluded those biosignatures were non-biological. Professor Niku Medusan's DocuVerse team acknowledges their finding falls short of the 5 sigma threshold. They describe themselves as cautiously optimistic, a scientific way of saying they think they've found something extraordinary but need more evidence. Achieving 5 sigma for K2118b would require 16 to 24 additional hours of observation, a significant investment in telescope time in a competitive schedule where every minute counts. The statistical challenge grows more complex, considering DocuVerse is detecting molecules across 729 trillion miles. Signals must traverse interstellar dust, cosmic radiation, and instrumental noise before reaching the detectors. Each of these factors introduces possible sources of error that could imitate an actual detection. Independent research teams have already started re-examining the DocuVerse data using different statistical approaches and atmospheric models. Some early analyses suggest the dimethyl sulfide signal may be weaker than initially reported, while others support the original conclusion. This scientific debate demonstrates the peer review process functioning exactly as intended, multiple teams testing, challenging, and verifying each other's results. The 3 sigma detection remains humanity's strongest evidence yet for possible extraterrestrial life, but it also highlights the immense difficulty of proving such a groundbreaking claim. We now stand on the edge of what could become the most significant discovery in human history, though the level of statistical certainty required still lies just beyond our reach. What's at stake is the answer to the oldest question of all: are we alone? Beyond the familiar rocky planets and gas giants of our solar system lies a new category of worlds that could completely transform our understanding of where life may exist. Hycean planets represent a cosmic hybrid, combining the deep oceans of water worlds with the thick hydrogen atmospheres found around many Neptunes. The term itself merges hydrogen and ocean, describing planets that operate under conditions entirely unlike anything in our solar system. These mysterious worlds challenge Earth-centered assumptions about what makes a planet habitable. K218b serves as the prototype for this new class of potentially life-bearing planets. Unlike Earth, where life thrives between a thin atmosphere and shallow seas, Hycean planets could host life within vast 3-dimensional ocean layers extending hundreds of miles deep beneath crushing hydrogen-rich skies. Think of Hycean worlds as cosmic pressure chambers, where extreme environments might actually promote certain forms of life. Their dense hydrogen atmospheres create surface pressures hundreds of times greater than Earth's. Yet this same pressure can stabilize liquid water at temperatures that would normally cause it to evaporate into space. The hydrogen-rich air also presents unique chemical opportunities. While life on Earth largely depends on oxygen-based metabolism, hydrogen-based metabolisms could support entirely different biochemistries. Some Earth microbes already display this ability, thriving in deep-sea hydrothermal vents where they draw energy from hydrogen sulfide rather than sunlight. Professor Niku Dusudan and his team proposed the concept of Hycean worlds in 2021, predicting that such planets could produce detectable biosignature gases like dimethyl sulfide. The recent DocuVerse detection of these exact molecules on K218b strongly supports their theory. These planets offer several major advantages over Earth-like worlds in the search for life. Their thick atmospheres produce stronger, easier-to-detect signals, and such planets may be far more common across the galaxy than small, rocky ones. This abundance could mean life has many more opportunities to evolve elsewhere. The immense size of their oceans adds another layer of intrigue. Earth's oceans hold about 1.3 billion cubic kilometers of water, but a Hycean world like K218b might contain many times that volume, enough to support massive, diverse ecosystems dwarfing anything on our planet. Their thick atmospheres also distribute heat efficiently, keeping global temperatures relatively stable. Unlike Earth, where poles freeze while the equator bakes, Hycean planets might maintain steady, life-friendly climates across their entire surfaces. The discovery of potential biosignatures on K218b suggests Hycean worlds deserve serious consideration in the search for extraterrestrial life. These alien oceans might represent our best chance of discovering biology that operates by entirely new rules. But what kind of life could survive in such extreme environments? In Earth's sunlit seas, trillions of microscopic organisms perform chemical processes that may mirror what's happening 124 light-years away. Phytoplankton, tiny marine plants nearly invisible to the naked eye, are among the most abundant life forms on our planet. A single drop of seawater can contain thousands of them, each a miniature chemical factory transforming minerals into the foundation of ocean ecosystems. They are so small that 50,000 could fit on the tip of a pin, yet together they generate more oxygen than all of Earth's forests combined. When phytoplankton process sulfur compounds dissolved in seawater, they naturally produce dimethyl sulfide as a metabolic byproduct, like a form of cellular respiration. Just as humans exhale carbon dioxide after burning sugar for energy, phytoplankton release dimethyl sulfide when they metabolize sulfur nutrients. This occurs on an immense scale. Marine phytoplankton pump an estimated 15 to 30 million tons of dimethyl sulfide into Earth's atmosphere annually, enough to fill around 12,000 Olympic swimming pools with pure gas. Once released, the molecule rises and plays a vital role in cloud formation and climate regulation. What makes the K218b detection remarkable is that on Earth, dimethyl sulfide typically measures less than 1 part per billion and breaks down quickly in sunlight, meaning it must be constantly replenished by life to sustain even those tiny amounts. Despite this, the DocuVerse telescope observed concentrations potentially thousands of times greater than those found in Earth's air. That implies either an extraordinarily powerful biological source continuously producing it, or an unknown chemical process that doesn't exist naturally on our world. Marine biologists have studied dimethyl sulfide for decades, discovering that various phytoplankton species emit it in different amounts. Some algae produce it when stressed by shifts in temperature, salinity, or nutrients, while others release it as part of normal metabolism. The similarity between Earth's phytoplankton and potential alien life on K218b raises profound questions about biological convergence. If life exists on that distant world, did it independently evolve the same metabolic pathway, or is dimethyl sulfide simply a universal chemical signature of life using sulfur-based processes? Research on extremophiles, organisms that thrive in harsh, high-pressure, hydrogen-rich environments, shows that many could easily survive conditions found on Hycean worlds. Some deep-sea microbes even prefer pressures and temperatures that would instantly kill most surface life. These connections between Earth's microscopic ocean life and potential alien biology make the K208b discovery one of the most fascinating and hopeful findings in the search for life beyond our planet. Hidden within the ancient glow of distant stars lies the key to decoding the atmospheres of alien worlds. revealed through one of astronomy's most refined investigative tools. Transmission spectroscopy turns every exoplanet transit into a cosmic chemistry experiment. When K218b passed between its star and Earth, it created a natural observatory where starlight became the probe and the planet's atmosphere served as the sample under examination. For a few brief hours, photons traveling across interstellar space carried with them the chemical fingerprints of an alien world. The process begins with a simple but powerful principle of physics. Every molecule absorbs light at specific wavelengths, forming a unique spectral barcode. Water vapor absorbs at certain infrared bands, carbon dioxide at others, and dimethyl sulfide at its own distinctive frequencies. When starlight passes through a planet's atmosphere, each molecule removes its characteristic colors, leaving dark absorption lines in the spectrum. Imagine viewing a streetlight through tinted glass. If the glass is red, less blue light reaches you. Similarly, when starlight filters through K28b's atmosphere, molecules in that alien air selectively remove specific wavelengths, revealing which chemicals drift in those faraway skies. Docuverse's revolutionary strength lies in its unparalleled sensitivity to these spectral signatures. Earlier telescopes could only detect the strongest features from massive, hot exoplanets. Docuverse, however, can measure changes so subtle they alter the total starlight by less than 1 part in 10,000, akin to noticing if a single bulb went out in a city seen from orbit. During K218b's transit, Docuverse compared the star's light when the planet crossed in front with data collected when it was to the side. The difference between the two revealed the wavelengths absorbed by the planet's atmosphere. This differential approach cancels most instrumental noise and stellar variability. Detecting dimethyl sulfide required pinpointing absorption near 9 micrometers, invisible infrared light carrying 20 times less energy than visible wavelengths. At this range, dimethyl sulfide produces distinct absorption features that are hard to confuse with other molecules. The precision necessary for this measurement pushes the boundaries of technology. Detecting dimethyl sulfide on K218b was like gauging the thickness of a human hair from 10 miles away, while correcting for atmospheric distortion, instrumental vibration, and cosmic interference. What makes transmission spectroscopy so powerful is its ability to measure molecular abundance directly. The strength of each absorption line corresponds to the number of molecules responsible for it. Stronger lines mean higher concentrations. This lets scientists build detailed chemical maps of alien atmospheres. Docuverse's observations not only confirmed dimethyl sulfide's presence on K208b, but also estimated its abundance, transforming theoretical speculation into measurable chemistry. Yet transmission spectroscopy uncovered more than dimethyl sulfide. It revealed an intricate chemical narrative about K208b's atmosphere. Docuverse detected abundant methane and carbon dioxide, 2 gases offering deep insight into this world's environmental conditions. These molecules act as atmospheric detectives, revealing clues about temperature, pressure, and ongoing chemical processes. Methane appears in far greater amounts than on Earth, where it's mainly produced biologically through digestion or decay. But in K28b's hydrogen-rich atmosphere, methane may form through entirely different mechanisms tied to its immense oceans and intense pressure. The coexistence of methane and carbon dioxide indicates a reducing environment, conditions where reactions favor hydrogen-rich compounds. Such chemistry could theoretically sustain metabolisms unlike Earth's oxygen-based life, suggesting possible pathways for survival in this alien sky. The carbon dioxide detection also reveals critical information about K28b's ocean-atmosphere dynamics. On Earth, oceans absorb vast amounts of carbon dioxide, stabilizing climate through chemical buffering. The same interaction may occur on K28b, implying vast oceans beneath its hydrogen-heavy atmosphere. But one notable absence deepens the mystery: ammonia. Although early Earth's atmosphere contained significant ammonia, K208b shows virtually none, despite conditions that should naturally produce it. This lack supports the idea that the planet's deep oceans dissolve ammonia before it can reach the upper atmosphere. The resulting combination, high methane and carbon dioxide with missing ammonia, matches theoretical models of Hycean worlds with global oceanic layers. It's like assembling puzzle pieces that form the image of an alien water world governed by unfamiliar chemistry. The methane to carbon dioxide ratio provides further insight into potential energy cycles. Many Earth microorganisms gain energy by converting methane to carbon dioxide, a process known as methanotrophy. If comparable biological reactions occur on K218b, they could represent an entirely new way for life to extract energy from its surroundings. Temperature data derived from DocuVerse's observations suggest that K208b maintains conditions where liquid water could exist despite orbiting close to its dim red dwarf star. Methane and carbon dioxide's greenhouse effects, combined with heat circulation within the dense hydrogen atmosphere, create a climate capable of stabilizing ocean temperatures suitable for life. Together, these clues paint K218b as a world governed by chemistry unlike anything on Earth, a place where exotic processes might nurture forms of life beyond our imagination. The evidence points to something extraordinary hidden within those alien clouds. The star K218b orbits glows with the faint, steady light of a red dwarf, a cosmic survivor built for eternity. These stars burn hydrogen so efficiently they can shine for trillions of years, nearly 100 times longer than the universe's current age. While our sun will fade in 5 billion years, red dwarfs like K2118 will still burn when even black holes begin to evaporate. This incredible longevity offers unique opportunities for life to arise and evolve. On worlds orbiting red dwarfs, biological evolution would have trillions of years to grow, adapt, and diversify, far beyond anything possible on our fleetingly young Earth. Earth's life has had only 4.5 billion years to transform from microscopic origins into intricate ecosystems. Imagine then what life could become if granted 200 times longer to evolve and adapt. K208b orbits its red dwarf star just 13 million miles away, around 1/17th of Earth's distance from the Sun. Around a star like ours, such closeness would incinerate any planet instantly. But red dwarfs emit far less heat, allowing liquid water to persist even at tight orbital distances. This closeness produces what astronomers call tidal locking, the same phenomenon that keeps our moon forever showing one face to Earth. One hemisphere of K218b remains in perpetual daylight, the other in endless darkness. Though this might suggest harsh temperature contrasts, the planet's thick hydrogen atmosphere likely redistributes heat, maintaining a stable global climate. Red dwarf habitable zones also remain constant for staggering lengths of time. Unlike our sun, which brightens as it ages and gradually pushes its habitable zone outward, red dwarfs maintain nearly steady energy output for trillions of years, creating unmatched cosmic stability for life. Because roughly 75% of the Milky Way's stars are red dwarfs, their systems could harbor countless habitable worlds. If life thrives around them, the potential number of living planets expands dramatically. K218b receives about the same amount of energy from its faint star as Earth gets from the Sun, keeping its surface warm enough for liquid oceans, the foundation of life as we understand it. The detection of possible biosignatures near K218b's red dwarf suggests these small, enduring stars may be our best chance in the search for extraterrestrial life. Yet proving it requires solving a chemical mystery within the planet's skies. Sometimes the absence of something speaks louder than its presence. On K218b, a molecule expected to be common, ammonia, is strangely missing. That absence may be the strongest evidence yet for vast oceans beneath the planet's hydrogen-rich atmosphere. Ammonia plays a vital role in planetary chemistry. Under K218b's predicted temperature and pressure, it should form easily through reactions between hydrogen and nitrogen. The planet's hydrogen-heavy atmosphere seems ideal, yet the James Webb Space Telescope detected almost none. Like a missing clue in a detective novel, this void reveals a deeper truth. If K28b had no surface oceans, ammonia would likely exist alongside methane and carbon dioxide. Instead, its disappearance suggests immense oceans absorbing it. Ammonia dissolves readily in water, especially under high pressure, turning global seas into powerful chemical sponges that strip it from the air. Earth's oceans perform a similar task, dissolving nitrogen compounds that would otherwise exist in the atmosphere. But on K218b, the effect would be magnified by oceans far deeper and more extensive than ours. This chemical pattern, methane and carbon dioxide abundant, ammonia scarce, fits perfectly with predictions for Hycean worlds, ocean planets shrouded in hydrogen. Dr. Subhajit Sarkar, a member of the research team, called the missing ammonia a smoking gun for the presence of deep liquid oceans. The findings imply not just shallow seas, but immense, planet-wide waters capable of reshaping atmospheric chemistry itself. This kind of chemical detective work highlights how modern exoplanet research has evolved far beyond simply identifying molecules. By examining the interplay between atmospheres, oceans, and planetary surfaces, astronomers can infer environmental conditions across unimaginable distances. The ammonia mystery elevates K218b from a mere data point to a vivid candidate for an ocean world beneath alien skies. Still, not all scientists agree. In astrobiology, the boundary between discovery and false alarm can shape reputations for generations. The reported detection of dimethyl sulfide, DMS, on K218b has ignited debate. Some interpret it as a potential biological marker, while others insist on more definitive evidence. Dr. Jake Taylor of Oxford University reanalyzed the Webb data using alternative models and concluded that the DMS signal might be far weaker than initially claimed, possibly lost within instrumental noise. Detecting molecular signatures across 729 trillion miles is extraordinarily challenging. Every photon that reaches Webb's sensors travels 124 years through cosmic dust and radiation, distorting the faintest details. History offers cautionary lessons. In 1996, a Martian meteorite was thought to contain fossilized microbes, an announcement later attributed to natural mineral processes, not biology. As Professor Sarah Seeger of MIT remarked, the findings from K218b are not yet proof of life, but rather a powerful reminder to refine our tools, our analyses, and our expectations. Docuverse. Her evaluation mirrors the scientific community's heightened caution after past false alarms, underscoring the importance of multiple independent confirmations before declaring alien life. The dimethyl sulfide debate also exposes deeper questions about what level of evidence should qualify as proof of biosignatures. Should researchers demand the 5 sigma threshold, the same statistical rigor used in particle physics? Or can the extraordinary implications of detecting extraterrestrial life justify accepting slightly lower confidence levels, balanced against the danger of false positives? Some experts suggest that unknown chemical pathways might occur within the extreme conditions of Hycean worlds, allowing geological processes to generate dimethyl sulfide through mechanisms not yet understood. The immense pressures, hydrogen-heavy atmospheres, and deep ocean chemistries of planets like K218b form environments unseen anywhere in our solar system, making it difficult to dismiss non-biological explanations outright. Dr. Teeming of UC Riverside noted that the strongest biosignatures on other worlds may differ dramatically from those common on Earth. This perspective implies that our Earth-centric expectations could blind us to genuine signs of alien biology that follow entirely different biochemical rules. The global debate continues as scientists scrutinize every subtle variation in the Webb telescope's data, searching for truth encoded in ancient light. In science, the 5 sigma mark defines the boundary between compelling evidence and confirmed discovery. Achieving 5 sigma confidence means there's only a 1 in 3.5 million chance that a signal is random noise rather than a genuine finding. To illustrate, you're more likely to be struck by lightning twice in 1 year than to see a false 5 sigma result. This strict standard exists because science has learned difficult lessons from premature claims later disproven. The Large Hadron Collider reached 5 sigma certainty before confirming the Higgs boson in 2012, analyzing trillions of collisions over years of data collection. Likewise, LIGO met the same standard before announcing the detection of gravitational waves from merging black holes billions of light years away. Applying that level of rigor to exoplanet atmospheric studies, however, presents unique challenges. Unlike controlled experiments that can be repeated endlessly, exoplanet transits occur only when orbital geometry aligns perfectly with Earth's viewpoint. K28b passes in front of its star every 33 days, limiting the opportunities for verification. The current 3 sigma detection of dimethyl sulfide sits below the gold standard, compelling but inconclusive. Reaching 5 sigma certainty would demand 16 to 24 more hours of Webb observation time, a major investment to confirm what could become one of humanity's most historic findings. Professor Niku Medusan and his team acknowledge this statistical gap, but argue that the public deserves to witness discoveries unfold in real time instead of waiting years for absolute confirmation. Madhu Sadan compared it to NASA's Mars missions, celebrating progress while accepting uncertainty about the outcome. The 5 Sigma debate also stirs philosophical tensions within astrobiology. Some contend that the monumental importance of discovering alien life warrants slightly relaxed thresholds when several independent lines of evidence align. Others maintain that extraordinary claims must always meet extraordinary proof, no matter how exciting the implications. Independent replication offers another route to credibility. When multiple teams, using distinct telescopes, models, and analytical techniques, detect the same signal, the combined evidence can approach 5 Sigma confidence even if individual efforts fall short. Future Webb observations of K208b, employing different instruments and longer exposure times, could provide the decisive data, either confirming the dimethyl sulfide signature or disproving it as instrumental noise. Until then, humanity remains poised between 2 possibilities. Either we've detected the first real sign of alien life, or we've witnessed the most convincing false alarm in the history of astrobiology. The answer still travels toward us in photons yet to arrive from that distant world. Deep beneath K218b's crushing oceans, if life exists, it must endure pressures that would annihilate any earthly organism. Yet those same extremes could foster biology beyond imagination. Forget what life looks like here. Beings on K218b might thrive through biochemical pathways unlike anything on Earth, producing dimethyl sulfide under pressures hundreds of times greater than our deepest ocean trenches in hydrogen-rich waters, beneath skies heavy with exotic chemistry. Such organisms could exist as immense, drifting colonies floating through the planet's boundless ocean layers. With no solid surfaces, evolution might favor complex internal frameworks, hydrogen-filled bladders, or magnetic navigation systems to remain stable and oriented. Without sunlight, photosynthesis would be impossible. Instead, these life forms might depend on chemosynthesis, drawing energy from hydrogen, methane, and mineral reactions. Imagine vast, translucent organisms spanning miles across, processing chemicals on planetary scales that dwarf Earth's largest creatures. Their biochemistry might rely on hydrogen-based solvents stable under immense pressures, creating unfamiliar metabolic cycles. Dimethyl sulfide could even serve as a communication tool, a molecular signal shared between species, forming global biochemical networks detectable light years away. Evolution on K218b might unfold over millennia, supported by the constant energy of its red dwarf star that burns steadily for trillions of years. Life could diversify in vertical layers, surface organisms interacting with the atmosphere, while deep-sea species draw energy from hydrothermal vents far below. If life exists there, it operates under laws entirely alien to our biology, yet perhaps still generates the same molecular trace familiar from Earth's oceans. The photons revealing this story journeyed 729 trillion miles, light that began its voyage 124 years ago, when Abraham Lincoln was president. Along the way, they crossed interstellar dust, magnetic fields, and gravitational distortions before reaching Webb's golden mirrors. Detecting their faint signals demanded precision beyond comprehension. The dimethyl sulfide absorption dimmed starlight by less than 1 part in 10,000, like spotting a single candle going out in a chandelier seen from the moon. Stationed 1 million miles from Earth at the L2 point, the telescope avoids atmospheric interference but faces micrometeorites, solar radiation, and cosmic rays that could mimic false readings. Maintaining stability to capture such minute variations requires instruments colder than Pluto's surface, cooled by complex cryogenic systems that must run flawlessly for years. This astonishing feat highlights both the fragility and power of humanity's quest to find life beyond Earth. Every photon Docuverse captures from K218b draws us closer to answering the oldest question of all: are we truly alone? Despite these seemingly insurmountable challenges, Webb successfully detected not only dimethyl sulfide, but also compiled detailed chemical inventories of K218b's atmosphere, identifying methane, carbon dioxide, and water vapor. This accomplishment ranks among the most technically demanding feats in the history of astronomy. The fact that we can detect possible indicators of alien life across such staggering distances demonstrates both the extraordinary precision of modern space telescopes and the universal physical laws that govern light and matter throughout the cosmos. Yet, this milestone has not silenced skeptics who question whether we are truly observing evidence of life. Following the K218b announcement, a growing number of scientists voiced a sobering reminder. Extraordinary claims require extraordinary evidence, and this one may not yet meet that threshold. Dr. Kevin Stevenson from Johns Hopkins University noted that many in the exoplanet field believe enthusiasm has outpaced the strength of the data in the dimethyl sulfide detection. His remarks reflect broader concerns within the scientific community about the risks of premature announcements that could erode public trust if later disproven. Skepticism intensified when multiple research teams attempted to replicate the Webb telescope results using the same data, but different analytical methods. Several of these reanalyses failed to confirm dimethyl sulfide, instead finding patterns consistent with instrumental noise rather than genuine atmospheric chemistry. These contrasting interpretations reveal how small variations in data processing can yield vastly different outcomes. Dr. Jake Taylor's reanalysis at Oxford University became particularly influential among critics. Using standard exoplanet analysis procedures, he found the data consistent with a flat spectrum rather than showing the molecular absorption features reported by the Cambridge group. His findings suggested that advanced statistical models might be detecting illusions in the noise rather than real atmospheric signals. The debate extends beyond statistics into the core of atmospheric chemistry. Some researchers pointed out that Webb's data failed to detect ethane, a molecule expected to appear alongside dimethyl sulfide if ultraviolet radiation from K208b's star were breaking it down. The absence of such byproducts raises questions about whether the detection reflects real chemistry or instrumental artifacts. Professor Laura Kreidberg from the Max Planck Institute emphasized that the strength of the evidence relies on subtle analytical details that, in her view, do not meet the bar for a convincing detection. Her critique suggests that the Cambridge team may have stretched their analytical tools beyond reliable limits while chasing an extremely weak signal buried in noise. This wave of skepticism draws on astrobiology's troubled history with false positives. Beyond the famous Martian meteorite incident, the field has endured multiple claims of biosignatures that later proved to have non-biological origins or resulted from experimental errors. These lessons have made researchers cautious about accepting extraordinary claims without overwhelming corroboration. Critics also argue that the Cambridge team's decision to publicize their findings before extensive independent review broke with scientific norms. Although their work appeared in a peer-reviewed journal, media announcements and press releases preceded thorough examination by the broader scientific community. The controversy has reignited fundamental questions about how science should communicate groundbreaking discoveries. Should world-changing results be shared immediately after reaching basic statistical thresholds, or only after multiple independent confirmations? The K218b debate exemplifies the tension between scientific rigor and public curiosity. As more teams reanalyze Webb's data with diverse methodologies, the consensus could shift toward either validation or rejection of the biosignature claim. Ultimately, new observations, possibly years in the making, will determine the truth. Humanity's most promising lead in the search for alien life now depends on whether follow-up studies confirm K218b as a living world or relegate it to the archive of false hopes. The Webb team has already secured additional observation time to re-examine K218b using alternative instruments and longer exposures. These follow-ups could either elevate the dimethyl sulfide detection to the 5 sigma gold standard or eliminate it as noise. The stakes are enormous. These results will decide whether we have truly found signs of life or encountered one of astronomy's most persuasive false alarms. Future observations will employ Webb's full suite of spectroscopic instruments, including extensive use of the mid-infrared instrument, MIRI, which yielded the initial dimethyl sulfide hint. By observing multiple planetary transits, astronomers can boost signal strength and verify consistency across events. One crucial test will be searching for other sulfur-bearing molecules, such as dimethyl disulfide or hydrogen sulfide, that should appear if biological processes are responsible. Detecting these would strongly support genuine atmospheric chemistry over instrumental artifacts. Scientists are also refining atmospheric models to predict what Webb should see if K218b truly hosts life. These frameworks will help distinguish biological from non-biological explanations, providing benchmarks for future data. The European Space Agency's upcoming Plato mission, launching in 2026, will deliver complementary observations of K208b and similar planets, offering potential independent confirmation. Meanwhile, ground-based facilities, such as the extremely large telescope under construction in Chile, will soon achieve unprecedented resolution for exoplanet atmosphere studies, possibly revealing spatial variations in chemistry that could validate or refute the presence of life. Astronomers are also expanding the search to similar worlds. If K218b's dimethyl sulfide detection represents a true biosignature, comparable signals should appear in other Hycean planets under similar conditions. Finding consistent molecular patterns across multiple worlds would suggest a widespread biological phenomenon rather than isolated chemistry. To that end, researchers have proposed specialized missions focused solely on biosignature detection, capable of studying dozens of habitable zone planets with far greater sensitivity than today's instruments. Resolving the K288b mystery could take months or years, depending on observation schedules and data strength. Each new measurement draws us closer to answering the most profound question in science: are we alone in the universe? K218b marks only the beginning of Webb's search for life, with dozens of potentially habitable planets awaiting atmospheric analysis that could transform our understanding of biology beyond Earth. Among them, the TRAPPIST-1 system stands as Webb's most ambitious target, hosting 7 Earth-sized worlds, 3 within the habitable zone where liquid water might exist. Unlike the hydrogen-rich K218b, these planets may possess thinner atmospheres similar to Earth's, allowing the detection of oxygen, ozone, and other biosignatures tied to terrestrial life. Initial Webb observations of TRAPPIST-1b revealed a bare, atmosphere-stripped world, but its neighboring planets, particularly TRAPPIST-1e, F, and G, remain promising candidates for habitability. Other high-priority targets include Proxima Centauri b, our closest exoplanet neighbor just over 4 light-years away, and TI 750b, a recently discovered super-Earth about 100 light-years distant. Webb's broader campaign spans not only Earth-like worlds, but also hot Jupiters, such as WASP-39b, whose atmospheres have already yielded rich chemical data. Many of these sub-Neptune and Hycean planets, larger than Earth yet smaller than Neptune, may host global oceans beneath hydrogen-rich skies, offering potential habitats for alien life. Even if K28b ultimately proves lifeless, the techniques pioneered in its study will refine methods for exploring dozens of other promising worlds. Over the next few years, Webb's exoplanet program will expand from isolated case studies to sweeping statistical surveys, potentially uncovering atmospheric patterns that reveal where and how life might arise across the galaxy. Each new world examined brings us one step closer to understanding whether life is a cosmic rarity or a universal truth. The confirmation of life on K28b would mark one of the most profound shifts in human understanding since Copernicus displaced Earth from the cosmic center. For millennia, humanity has looked to the stars, wondering if we are alone. Every culture, religion, and branch of science has wrestled with this question, yet we've remained limited to a single data point: Earth, the only known living world. Detecting biosignatures on K28b would expand that sample to 2, forever transforming our understanding of life's place in the cosmos. Such a revelation would send philosophical shockwaves through every aspect of human thought. If life independently arose on K218b, it would imply that biology is a natural outcome of planetary evolution rather than a cosmic fluke. Earth would no longer stand as an isolated oasis of life, but as one of countless living worlds scattered across the galaxy. Religious and spiritual ideologies would face unprecedented challenges about creation, consciousness, and divine purpose. Some belief systems might see alien life as confirmation of a life-generating universe, while others could struggle to integrate it into human-centered doctrines. Science itself would pivot dramatically toward astrobiology and comparative planetology. Understanding how life could thrive under K218b's extreme conditions would demand breakthroughs in biochemistry, planetary science, and evolutionary theory. Universities might found new research centers dedicated entirely to non-terrestrial life, while global space agencies would prioritize missions to habitable exoplanets. The economic ripple effects could be equally transformative. Technologies invented for detecting alien life might revolutionize medicine, environmental sciences, and industrial innovation. The space sector would enter a new golden age as nations and private firms compete to study living worlds beyond Earth. Culturally, humanity would need time to absorb the implications. Science fiction would become science fact, forcing people to confront the real, not imagined, existence of alien organisms. Art, philosophy, and literature would explore what it means to share the universe with other forms of life. International cooperation in space research would likely strengthen, recognizing that the exploration of alien life surpasses the capacity of any single nation. The discovery of life on K218b could drive humanity toward unified efforts in interstellar observation and exploration technology. Perhaps most profoundly, it could reshape how we see Earth itself, one living world among many, yet uniquely ours to protect. Such awareness might inspire a deeper commitment to preserving our planet's biosphere, while offering hope that life's resilience extends far beyond our solar system. Psychologically, reactions would vary. Some might feel insignificant. Others, inspired by the knowledge that life thrives in unexpected corners of the cosmos. Either way, confirmation of life on K218b would represent a milestone equal to agriculture, industrialization, or the scientific revolution, a turning point in our story as a species. Whether or not K218b truly harbors life, this discovery has already redefined how we search for it among the stars. The analytical techniques used to study K218b's atmosphere represent a quantum leap in our exploration of distant worlds. DocuVerse's demonstration that we can detect molecular fingerprints in an exoplanet's air from hundreds of trillions of miles away has opened doors once confined to science fiction. Future telescopes will refine these methods, mapping the chemical compositions of potentially habitable planets across our galactic neighborhood. The Hycean planet concept has emerged as a revolutionary idea, revealing that hydrogen-rich oceanic worlds may be far more common and easier to study than rocky Earth-like ones, potentially multiplying the number of worlds capable of hosting life. Even if dimethyl sulfide proves to be a false alarm, the analytical, statistical, and modeling techniques developed in this research will permanently enrich humanity's toolkit for detecting life elsewhere. Each misstep teaches as much as each success. The global scientific collaboration surrounding K218b exemplifies how the search for life transcends borders and ideologies. Teams across continents have joined in testing, confirming, and questioning the results, creating a united scientific network driven by a shared purpose. Upcoming space observatories will surpass DocuVerse's current power. The planned Habitable Worlds Observatory, for instance, aims to directly image exoplanets, analyze their atmospheric chemistry, and even detect seasonal variations that could indicate living processes. On Earth, next-generation telescopes like the Extremely Large Telescope will deliver ground-based observations with unprecedented detail, complementing space missions. The excitement around K208b has also reignited dreams of interstellar travel. Though still far beyond today's propulsion technology, the mere possibility of confirmed alien life fuels the drive to develop new systems capable of reaching nearby habitable worlds. Artificial intelligence is now accelerating these discoveries, identifying subtle spectroscopic signals that might otherwise be lost in noise, revealing potential biosignatures on worlds once dismissed as barren. Over the next decade, dozens more exoplanets will be examined for signs of life, building a database that could show whether biology is rare or common across the universe. Regardless of what future data ultimately reveal about K218b, the planet has already earned its place in scientific history as the first world to teach humanity how to detect the breath of alien life across interstellar space. The era of exoplanet atmospheric archaeology has begun, and with it, perhaps the slow end of our cosmic solitude.